Continuing with Chapter 1 on equations and inequalities, we're now in Section 1.3, complex numbers and quadratic equations in the complex numbers system. So we're going to talk about what complex numbers are, and I want to make a note here that complex numbers include real numbers and, what we're going to learn about now, imaginary numbers or non-real. I want to make sure you understand that complex is the big umbrella. All the numbers are under that, not just the ones we're going to look at here. Now, quadratic equations in the complex number system, that means we're going to return to quadratic equations, but when b squared minus 4ac is negative, we're going to find out what we can do with that. We will continue on if we're told to solve in the big umbrella, the complex number system. One property of a real number is that its square is non-negative. If you take a real number and you square it, doesn't matter what it is, positive or negative, you get a non-negative number when you square it. So there's no real number such that x squared equals -1. To remedy this situation, we introduce a new number called the imaginary unit, which we denote with this lowercase italics I, and it's the number whose square is -1. That is, I squared is -1. Take the square root of both sides, you get I equals the square root of -1. So now we'll know what to do when we have a negative under the square root, because you can always factor out a -1 from any negative number. Complex numbers are numbers of the form a plus bi, where a and b are real numbers. The a part is called the real part of the number a plus bi. B is called the imaginary part, and I is called the imaginary unit. When a complex number is written in the form a plus bi, where a and b are real numbers, it is said to be in standard form. That's our standard form for a complex number. Any number of the form bi, what does that mean? It doesn't have the a. It doesn't have any real part at all, so it's called the pure imaginary number because it's only got the imaginary part. Again, note that all real numbers are complex numbers. Real numbers are complex numbers, imaginary numbers are complex numbers. So let's explore powers on I. Okay, I to the first power, of course, would just be I. I squared, we have defined I squared as -1. But what's I cubed? Well, let's investigate by breaking that down. I could write that as I squared times I to the first. I squared is -1. I get -I. So I cubed is -I. What's I to the fourth? Well, I could break that down to I squared times I squared. That's I to the fourth. Each I squared is -1. And -1 times -1 is +1. I to the fifth. We'll break that down. How about I to the fourth times I? Because now we know what I to the fourth is. I to the fourth we said was 1 times I. So we've got I to the sixth. Well, we could do that as I to the fourth times I squared, because we know what both of those are. I to the fourth is 1. I squared is -1, so we get -1. What are you noticing about the pattern here? We had I, -1, -I, 1. I, -1. What do you think the other two would be? -I and 1, right? So what we notice is that powers of I repeat every fourth power. Powers of I repeat every fourth power. So if we know the pattern of the first four, then beginning with 5, all we have to do is I'll show you, if we divide the power by 4 and take the remainder, that's your new power on I. So let's look at some examples here to see how that's going to work. But for example here, if I divide 5 by 4, the remainder is 1. I to the first, look, I to the first. Divide 6 by 4, the remainder is 2. I squared is -1, and that's what we got. So let's try that here. For 23, let's do, I've got some more space down here, so I'll do it down here. So 4 into 23 goes 5 times, and I get a 3 remainder. So that means I to the 23 is the same as I cubed, and we know I cubed is -I. So I to the 23 is the same as -I. 4 into 37 goes 9 times with a remainder of 1. So this is the same as I to the first. 4 into 30 goes 7 times with a remainder of 2. So this is the same as I squared, which we know is -1. That's the definition of I squared. And 4 into 44 goes 11 times with a remainder of 0. So what's I to the 0? What's any number raised to the 0? Any non-zero number raised to the 0? It's 1, right? So that's where we had our 1 right here. When we divide 4 by 4, we have no remainder, right? Okay, so that's the trick for doing any power of I. Divide the power by 4, and then raise I to that remainder, and it's either going to be 1, 2, 3, or 0, and you know your pattern there.